Okay, now I want to talk about derivatives, but I don't want to define derivatives, I just want to talk about what kind of thing they should be, at least. So let's recall how it works in one dimension, where we have actually defined things. So if you have f maps an interval ab to r, then what kind of thing is f prime, assuming that f is differentiable everywhere? Just what type of thing is f prime? Well, it's a map from AB to R also. So it's the same type of thing. If you take the derivative of a map of this type, then you get another map of this type. Same domain. And in particular, if you focus on the derivative at a specific point, then that's going to be a real number. That's the kind of thing that it is. What it does is it tells you roughly how to know how the output of f changes when you know changes to the input. So people say things like this, I guess. If I want to be a little bit more precise, maybe I'll write it like this. Since, okay, so if x naught is in there, then the thing called f prime x naught is the limit of fx minus fx naught over x minus x naught. That's as x goes to x naught. So I just want to rewrite this in a way that shows you that it's allowing you to approximate delta f in terms of delta x. So let me subtract f prime x naught to the other side. And that, I mean, this is just a constant as far as the limit is concerned. So let me just write it like this. Fx minus fx naught, x minus x naught, and then I'm just subtracting this to the other side, and I can include it in the limit. It's just a constant, and as long as the limit exists, these things are the same. This is harmless. And I can also merge it kind of into this fraction by doing this. Subtract f prime x naught, x minus x naught. And then I can think of this limit statement, that as x goes to x naught, this thing goes to 0, as telling me that the numerator, I mean, this is a situation where the numerator and the denominator are both going to 0 as x goes to x naught. I can think of this as telling me the numerator is going to 0, not just going to 0, but going to 0 fast enough to beat this. So you might express that statement like this. So let me just use this terrible wiggly equals 0 to say that this is close to 0 when x is close to x naught. And more than that, it gets close to 0 when x gets close to x naught so fast that even if you divide it by x minus x naught, then that fraction still goes to 0 as x goes to x naught. So this is what I'll mean temporarily in this discussion by wiggly equals 0. Okay, so another way to write this is like this. Fx equals wiggly equals fx naught plus f prime x naught times x minus x naught. Or, you know, I'd rather actually write it like this. Fx minus fx naught, wiggly equals this thing. So wiggly equals, again, means this becomes more and more true. This becomes more and more of an equality as x goes to x naught. All right, so let me summarize that up here by this kind of statement, that delta f, so let's call this, let me write the whole thing, fx minus fx naught is approximately f prime x naught x minus x naught. So here's how I'd rather write this. Delta f, thinking of delta f as how f changes as I change x from x naught to x, is approximately f prime x naught delta x. Okay, so this is kind of what you intuitively should be thinking of when you're thinking of derivatives. Okay, this is just giving the idea, and I'm not really trying to put down a precise definition for the higher dimensional case. I just want to focus on the types of things that we get. So here, this is a real number. It's being multiplied by a real number, that's x minus x naught. And here we have a real number, fx minus fx naught. And the wiggly equals means there's really some limit business going on, and I'm just not writing it down. Okay, let's upgrade to higher dimensions and think about what types of things different things should be. So suppose, for the domain, suppose I have omega, this is the notation Verdin seems to like, subset of Rn. And f maps omega to Rm. So the domain of f is some subset of Rn, and f is a function you could say with m components. Then what kind of thing should f prime be? Well, the derivative of f it should be a function that when you give it a point, gives you the derivative of f at that point. So it should itself be a function on omega. But then what kind of things should it output? So what should go here? So this part is the same, kind of. The domain stays the same if the function is differentiable everywhere. If the function is not differentiable everywhere, maybe the domain shrinks. Okay, but what goes here? What kind of things come out? So say x naught is in the domain, then what kind of thing is fx naught, f prime x naught? So what kind of thing comes out? Well, I mean, it can be whatever we want. We get to make the definitions, right? But there's a definition that goes with the theory of derivatives, which is the one we're going to use. So what's a good definition? The essence of what a derivative is that it should tell you how the output of a function responds to changes to the input. So it should map input changes to output changes. Just like this number in the one-dimensional situation, this number tells you how input changes correspond to output changes. If this number is 2, then it's telling you increasing the input by 2 increases the output. It tells you increasing the input by a certain amount increases the output by twice that amount. So that's what this number does. So here, how can I express an input change? It's still this idea of x minus x naught, except x and x naught are going to be object with multiple components. So these will be in Rn, where n is the dimension of the domain. So whatever this is, it's going to have to operate on delta x's that are vectors with n components. And the reason is that it's these kinds of vectors, it's these kinds of objects that tell you, that describe displacements from x naught. So you look at the input x naught and you're like, I'm going to change it to x. Then x minus x naught, that displacement vector, is going to be the vector that represents the modification that you have made to the input. Then what kind of object represents the modification that results on the output side? So what you might call delta f is fx minus fx naught. But the outputs of f are vectors with m components, so these live in Rm. That means this is a vector. So let me put an object with multiple components. That's what I mean by that. So this is an object with m components. So whatever this is, it should still fit in a statement like this, that the output displacement vector should equal the input displacement vector with this thing, whatever this thing is, applied to it. So if this is a vector with n components, here this is an n tuple, this is an m tuple, then this must be some kind of mapping from Rn to Rm. And sorry, this should be a wiggly equals. Again, which just means there's really limit stuff going on and I'm just trying to ignore it for the moment. Just to focus on the types of things. So now we know the type of thing that this is a map from Rn to Rm. That is what it has to be. That's interesting. So over here, f prime x naught was a real number. Now f prime x naught has to be something that turns n tuples into m tuples. And we will demand that it be linear. And that's the essence of differentiability, is the existence of a map that works like this, with the appropriate limit statements in place, and which is linear. It has to be a linear approximation to the function. So it tells you to first order, or to some kind of, to linear order, how the outputs of the function respond to changes in the input. Okay, so now we can answer the question here. F prime, assuming whatever limits are needed to exist, f prime is going to be something that turns points in the domain into linear maps from Rn to Rn. So let me get the clutter out of the way for a sec and just look at what has happened. Back here, in the one-dimensional situation where you have one-dimensional input, one-dimensional output, when you take a derivative, you're used to having the same kind of function. You know, and you can keep taking derivatives. Like you can talk about the derivative of this and the derivative if they exist. You know, you can talk about taking a derivative 117 times and it'll still be a function of this type. But here, something is really different. Taking a derivative of a function mapping omega to Rn gives you something that seems to have a totally different type signature. And this is the start of, hopefully you're starting to see what will be really different when we study derivatives of these kinds of functions. But I also want you to see that it's not that different. This is still a mapping from real numbers to real numbers. But what is being used is the fact that linear mappings from real numbers to real numbers are just like real numbers. So as a vector space, this is basically the same as that. Now, if omega is a subset of Rn, omega is a metric space. If we end up with something like this, now this is a metric space since we've given it a metric. So hopefully now you are seeing why we might want to be able to treat this as a metric space.